Professor Monica Katiyar. So Monica Katiyar is part of Material Science and Engineering, the faculty there, and she is also heading the Flexible Electronics Division. She did her BTech from IIT Kanpur, and then she did her Masters from McMaster University, and then PhD from UIUC Chicago. She has more than 30 years of teaching and research experience as well as industrial experience. Her area of interest are electronic material and devices, organic electronics, thin film transistor, memory devices, solid state lighting, sensors, printable electronics, and spintronics. So, Madam Anar.
Okay, thank you. First of all, thank you, Professor Jain, Professor Ramkumar, for inviting me to give this lecture. This is a lecture in the course of micro manufacturing. So, I think it should start with where do you think you can use thin films in micro manufacturing? Where you would find the use for this in micro manufacturing, or how would you use it in micro manufacturing? These are the questions that will come to mind, right? Generally, we have a course in our department, Thin Film Physics and Applications. So, it is a whole semester course, and I have 1 hour to sort of give you a brief on what it is. So, normally I start with my course with this is a new paradigm of manufacturing. At least 30 years ago, when we were learning manufacturing, we did not learn this as a technique for manufacturing. So, I start with my course saying that if you had to use conventional manufacturing techniques, what is the thinnest material you can make? What is the limit of the thickness that you can use using conventional rolling or any other technique? What do you think the thinnest material that we can make if we did not have thin film deposition technique by conventional techniques? What is the limit of the rolling process? How thin can we go? I mean, we do make foils. They are made by conventional techniques, right? We make aluminum foils. And then if you are going into plastics, you can even make things even thinner by rolling and extrusion processes, right? So, today even in conventional processing, you can get to very, very thin areas. When we were probably studying 30 years ago, it was still maybe in microns or 300 to 1000 micron, but today even in conventional manufacturing has advanced to the point that you can make very, very thin sheets of metals, of polymers, and that's an advancement in itself. But the thin film deposition allows you a range in which you can still not reach by conventional technique. The range it allows you is you can make a single monolayer of a material. Of course, it can't be freestanding, but if you have a base, you can make a single monolayer. A single monolayer means what? It should be having a thickness of an atom. You can make a film which is as thin as a thickness of an atom. That is possible by this technique, and you can also go to the higher extreme and you can make maybe microns thick. The techniques that I am going to talk about, they are not meant for more than that. The materials can be made which is one monolayer, few angstroms, to maybe microns thick. Beyond that, if you have to use, you will not use these technique, you will use some other technique like spray coating or some other things, right? And that is the difference between thin film deposition technique and I would call it thick film deposition technique. Okay, so the range we are talking about is starting from few angstrom to maybe a micron is these techniques are. So, I will just give you tell you briefly what in the course we do. So, in the course we start with this is the course starts with introducing the thin film technology, which is an important manufacturing process for a wide range of industries, right? And this is something which you will find in many industries today because of this possibility that you can make this range of films on a particular base. You can make thin film of any material. It is not limited to metals or ceramics or polymers. You can make thin films of any material. So, it is very versatile technique. We discussed different deposition technique in that course, and also what is the science behind that technique at different aspects. Okay. So, in this 1 hour I will try to sort of give you maybe the basics of what I discuss, and I have picked up among the other techniques physical vapor deposition technique to go into a little bit more detail because the 1 hour will allow only that much time, right. So, just let me in the course the techniques that I follow, I go into applications, what kind of applications where you would requiring these kind of techniques. Then surfaces, characterization, the science which goes into these thin film deposition techniques. I have some references here if you would like to read more. There are some books over here. I have also given some journals which are basically dedicated to thin films. There is thin film, thin solid film, surface science, applied surface science, Journal of Vacuum Science and Technology. They are all dedicated to processing and characterization of thin films and how they will be used. Okay. So let us start the discussion here. Okay. So how do we make these thin films? Compared to the conventional manufacturing, where normally you start with the bulk of the material, right, all the extrusion, rolling and all these, and then you try to bring it down to a very thin stage. This starts from the other side. The techniques we are talking about are saying that we will start from very basic, which is like atoms or molecules, and we will assemble them together in a form of a film. Okay. So we are basically in manufacturing, we are starting from the other end. Rather than taking a bigger thing and thinning it down to what we desire, we are starting from the other side, saying we will make the material in the form of its constituents, atoms, molecules, ions, whatever it is, and we will make them assemble in the form of a thin layer. That is how the difference in this technique is and why we talk about it differently. Now we can do this predominantly two ways. One is the constituent that we start are in a vapor phase. They are basically gaseous phase, atoms, ions, molecule clusters. We make a gaseous phase out of it. The second thing is we could also start from a liquid phase. Okay. Now liquid phase thin film deposition techniques is also an area to learn, but for today's talk I am concentrating basically on the vapor phase techniques, where the starting point would be the vapor phase. Okay. So that's why I given the title that we will talk about the physical vapor deposition, where from the vapor we will get to the thin film point. Now physical vapor deposition is the production of a condensable vapor by physical means and subsequent deposition of a thin film from this vapor. So in this technique, the vapor itself is created by a physical process, and then it gets deposited on a base or a substrate. We normally refer to it as a substrate in this area. Okay. As opposed to physical vapor deposition, I will briefly touch maybe towards the end if time permits. Chemical vapor deposition is different because that allows reactions. So physical vapor deposition is an area where we say there is no chemical reaction taking place during the formation of the film, only the physical processes are taking place. Okay. So that's the difference. So all thin film deposition technique broadly can be divided into vapor phase technique and liquid phase technique. Here we are concentrating on vapor phase technique. Within vapor phase technique, we can divide them into physical vapor deposition and chemical vapor deposition. Now physical vapor deposition will not involve any chemical reaction during the formation of the film, as opposed to chemical vapor deposition would involve a chemical reaction, right. And then there is a huge range of technique which actually do not fall into any two categories, they are in the middle. They have some physical vapor deposition characteristics and also some chemical reactions, right. So if I were to write all possible techniques, it would fill up a page, right, but I am just broadly looking at some basic ones which would form the physical vapor deposition, right. So in the basic techniques, it will be evaporation of material that will give a film, sputtering and reactive sputtering, and let us see how much we can cover today. So we will start with evaporation, which is the simplest way of making a film. And if one needs to look a little bit of history, when did people start thinking of this as a manufacturing process, depositing film as a manufacturing process? Any guesses? This area of materials manufacturing started. The first thin film was observed in the tungsten incandescent bulb. People were making these tungsten coils for the bulb, and then they realized that when they light up the bulb, there is some sort of a blackish thing that gets deposited on the glass. And that was the first realization that if you evaporate the material, you can make a film. Of course, they did not want it and they wanted to avoid that, But that was the first realization that if you evaporate material, you can go back and form a thin layer out of it. Okay? So, and that's early 1900s. So, I mean this area has grown in last 100 years from that first observation to becoming a manufacturing technique by itself. Okay? So, in this technique, right now the source material is heated in order to increase its vapor pressure. We allow the vapor pressure to expand into the evacuated container, and then we condense it onto the substrate. The partial pressure of the desired film material, whatever we want to deposit in the gas phase, must be equal to or larger than its vapor pressure in the condensed phase at the desired growth temperature. That is what the simple logic would say. If I want something evaporated, then that partial pressure should be higher when I evaporate it, and it will condense then wherever the temperature is lower, right? Just this normal evaporation condensation, if the temperature is higher at some point, it will evaporate, and at some other point, if I cool it down, then the vapor will go there and get deposited. So, that's in simple manner, that's how evaporation works. I heat up something, partial pressure goes up, and then it forms a partial pressure of the material. I have another surface which is at a lower temperature, and that vapor then goes and condenses there. That's how the thermodynamics of the technique works. So, there are 3 steps to the evaporation. The first step is generation of the depositing species, which can be just heating the material, thermal evaporation, or E-beam evaporation, or laser evaporation. So, depending on how you generate this material, each technique gets a name, right? So, if you were heating just thermally by some coils or something, it's thermal evaporation. If you are heating the material by shining an electron beam on it, it becomes E-beam evaporation. If you are heating the material by shining laser beam on it, it becomes laser deposition. So, how you create that species which will form the film will decide a particular technique. The second step is the transport of that species from the source where you created the species to the substrate where you will form the film. Okay, so, that is the second step in this thing, and that itself can have many variations, right. So, first step can have many variations, second steps can have many variations. You can insert a gas while the evaporation is taking place, you can plasma while evaporation is taking place, and again that is another variation into the technique. So, I was mentioning there are a large number of techniques, it is because of these variations. So, every time you make a variation, you give it a new name, right. So, if you put something in the step 2, you call it reactive evaporation rather than evaporation, right. So, do not get confused with many names, it is basically same technique a little bit modified. If modified is step 1, step 2, step 3, you can have a different name that goes with it. The step 3 is the material goes to the substrate. Now, these are atoms, right. So, these atoms have to now condense and form a film, and that is where the basic materials point comes in, how these films nucleate or grow to form a nice continuous film, and that is the step 3, and that requires information about the surface on which you are depositing, the energy of the atoms which are coming to the substrate, what is their energy, and what is the substrate temperature. Okay. So, I will get into a little bit more detail, but these are the 3 basic steps in having a film being produced by thermal evaporation. A very simple typical thermal evaporator would basically have a chamber, and a very important part of it is that we do the evaporation in the vacuum. Okay. Now, there are many reasons for doing it in vacuum. One is you can create the partial pressure for deposition at a much lower temperature than if we were to do it atmosphere. That is one reason. Second reason is if you heat it up something at atmosphere and evaporate it in the form of atom, it will immediately react with the oxygen around it or the atmosphere around. Okay. So, if you want to deposit, let us say pure aluminum, and you are doing it, if you just evaporated it in the air, it would immediately form aluminum oxide. So, you need to keep the purity of the material you are evaporating. So, that is the reason for evaporation. For electronic applications also, the surface needs to be very clean. So, if you do not do it in normal in vacuum, then the surface gets contaminated and you do not get a nice binding, right. So, from manufacturing point of view, you are depositing a film on a surface, right. So, if any contamination is on the cleanliness of that surface is important. If there is any contamination on that surface and you bring the vapor phase and it gets condensed on that, the strength of that joint between the substrate and the film depends on how the cleanliness for that interface is. So that is something which is very important when you are doing thin film deposition to maintain the surface or to make the surface proper. So in a typical system, you would have vacuum, and it depends on your need and what kind of application you are doing, to what vacuum you take it down. So it will have pumps, the voltage supply, temperature controller. This is a thermal evaporator. So the material is kept here. It is heated using resistive heating. The material gets evaporated and it is going everywhere in the vapor phase. This is where I put my substrate holder. I monitor the temperature for the substrate holder. I can control the temperature of the substrate, and whatever vapor is being created gets deposited on this substrate. And depending on how much thickness I want, I can control that, right? And as I mentioned, I don't want to get more than few microns in this case, because then there are other problems. If you are wanting some larger thickness, the films can peel off because of the stresses that are generated during the deposition. So there are other issues that one needs to look at if you want thicker films. This is basically the same thing, a little bit more detailed. Basic steps, what is it required in thermal evaporation. So step 1 is creation of deposition species, step 2 transport, and 3 is how the film is being formed on the substrate. This is another point which says, so now there is a lot of science that goes into it. You can actually calculate what will be a deposition rate based on, this is if you heat up a material, this is the flux of vapor phase or atoms, let us say in the case of thermal evaporation of metals, number of atoms per centimeter square per second which are coming to your substrate, and that is decided by the thermodynamic property of the material you are evaporating, the pressure in the chamber, and the temperature of the source material, okay? And that will be the mass, the thing that you are evaporating. So controlling the pressure, you can control this is the partial pressure of the material that you want to evaporate, okay? So if you have a material which has high partial pressure, it's easy to evaporate. The more high temperature metals you take, it will become more difficult to evaporate, and then you may have to go to E-beam deposition, because you can't just give it enough heat to get to a temperature where the evaporation is possible. So so one can calculate the flux of atoms coming to the substrate per centimeter square per second, and from there one can actually get a deposition rate. So this is the kind of science people do when they are depositing something. They try to control and see, if I change temperature, how much my deposition rate is changing for the film. So this is the manufacturing parameters that you can control here. So for thermal evaporation, you basically use resistive heating. Current is used to get the heat using the Joule heating, and the material is melted or sublimate the sample. It can be done using clips on wires or boards. I have some probably example to show how it works. The equation somehow got dropped. So this you can also calculate from using the gas kinetics theories, what is the flux that you will be getting from a particular source. You can even design something which is called a Knudsen sources, where you try to use put the material in a closed container with only a very small opening to try to give a thermal equilibrium situation if you want to control the evaporation rate very, very well. And this is a very important point. If I just evaporate something and I don't control its temperature, if I heat it, let us say I put a heater and I am heating the material, right? My evaporation rate will have a curve. It will first initially start slowly, then it will go to a higher value. As the material gets reduced, it will again come down, okay? So how am I controlling my flux as a function of time while the film is getting deposited is changing with time, which is okay for some applications. Suppose I am a particular application I can talk about is I want a mirror finish on a glass, right? I just want some aluminum or silver deposited on the surface. I don't really care what the deposition rate is, as long as my thickness, final thickness is some 300, 400 nanometer, I will just deposit it. But then a certain application, especially electronics application or optical application, where I want exactly, let us say 20 angstrom. Now if I want that 20 angstrom, I must control the flux of my evaporation very, very well, and the control of it in terms of manufacturing is the key. And the techniques like molecular beam epitaxy. It comes from all the technology that goes into creating that source where you can control the deposition rate. You control the temperature within 0.1 degree centigrade or so that your deposition rate, the flux that is coming out is very well controlled, and that's basically technology. So just evaporating something, getting a deposition is one case. The second is having a control so that I know that I am depositing 1 angstrom per minute, let's example, right? In which case I need to control my source. And today there are techniques and there are tools which people have developed that can give you that kind of control, and that's completely into manufacturing regime, how you manage that control. So, that kind of sources are there which are closed, and the temperature is monitored within a fraction of a degree centigrade, so that your source always gives you a controlled amount of deposition rate. These are some, if you just want some sort of evaporation, you can use even some tungsten coils for evaporation. You can just hang some aluminum wires on it, heat it up, it would just evaporate and give you a nice film. So these are simple example. On the other end is the very controlled one, which runs into crores to buy a equipment which has a very controlled evaporation rate. So you have the whole range of equipment depending on the control that you want. I'll just skip this. This is showing some calculation on how would you know what kind of heating element you want depending on what material you want to deposit, right? So depending on what temperature I want to take the material to, I should decide my heating element, the resistivity of the heating element. So I'll just skip that now. That's just a calculation for, and somehow the numbers are missing, or maybe it's not in a right color. But anyway, the point here is that you can make some estimates on what is the heating element that I want in order, if I have the material, and I can also make an estimate what kind of deposition rate I will get based on the gas kinetics theory. I can use the thermodynamics. For materials which have high melting points or the vapor pressures are low, rather than using thermal heating, one uses an electron beam, and the electron beam is directly incident on the material where it heats up locally and takes it to a higher temperature to create the vapor pressure, and that would be known as the E-beam evaporation system. Yes.
And what is the bonding between that coating and the substrate surface?
I am coming to that. That will be in step 3. Okay. So after you have created the source first, then the source has to travel from where you created it to the substrate, right? So we'll come to the third part about the bonding. Now here again, I think kuch problem ho raha hai. Maybe that's in a different color. That's why it's not showing up or something. I'll correct that. So the vapor transports in the step 2, the mean free path should be such that you can calculate from the pressure that the distance from source to substrate, that there is no interaction with the vapor. It should not interact with something. Other variations can also be important in this case. I've already explained why vacuum is required, because if you want purity of the metal you want to deposit, you need to have the vacuum there. Now I come to the third part, what kind of bonding is going to happen at the surface. So bonding will be decided by what is first of all cleanliness of your substrate. Suppose you have a very clean substrate, which means there is no oxygen or water vapor deposited on it, and that's a very important point. And I spend only a lecture or so in my course on this. If I take any surface here right now, how long do you think, and I clean it, let's say I take a silicon, right? If you take silicon and if you dip it in HF, it would remove all the oxide on it, and when you take it out of hydrochloric acid, it will be a silicon clean surface with atomic silicon on it. I bring it out and I keep it in this atmosphere in this room. How long do you think it will take before a nice 10 to 15 angstrom oxide is deposited on it? In the room temperature, just in the room. Huh? You have any idea? It will be quickly. Yes, it is very quickly. So in microelectronics, when you want to do, when you want to make gate oxide, which is silicon oxide on the silicon substrate, the HF cleaning of the silicon and the oxide deposition, the time gap that is allowed is about 15 to 20 minutes. If you don't do it within 20 minutes, you would have deposited a native oxide on it before you deposit your oxide. Okay. So, this is an important point. If you have a clean surface, if you have maintained it, and that is why as soon as you clean it, you put it in under the vacuum, because under the vacuum to grow the same surface, it would take maybe a day or so. So, you have enough time to bring in your material and deposit a film. Okay. So, that is the first point, your surface should be cleaned for a good bonding. Now, if I have maintained that as soon as I clean the surface, I have put it in vacuum and I have started my pump, and the surface remains clean for a few hours or something, and one can do the calculation using gas kinetics theories on that. Now, if I bring, let us say I am depositing silicon oxide, I bring silicon and oxygen atoms together and they will be deposited on this surface. The bonding in this particular case between silicon and silicon oxide is going to be the bonding which is there in silicon oxide, the covalent bonding. So, if the cleanliness of the surface is maintained, the silicon which is coming with the thermal energy which is getting deposited on the surface will be a covalent bond. If you bring in atom which is not reactive, then it would be van der Waals or some other force. But if you are keeping the cleanliness and the atom is coming with enough energy, you do get regular bonding, good metallurgical bonding as you say it, between the substrate and the film. But it all depends on these parameters. Okay. It is opposite to where you would say what is the bonding in a spray coated film. In a spray coated film, you bring in the spray or the droplets of whatever you are spray coating, it heats up to a certain temperature and it comes to the surface and just gets spread out, right. This is a mechanical bonding as we say it in thin films, right. Here it is metallurgical bonding as much as you can keep your surface clean. But if the surface has contamination, it has organic molecules and other things in that, then that bonding will not happen and you would have a less of a strength in that interface. Okay. So, you can really manage your bonding of the two interfaces depending on how you do the processing. Okay. Okay, so now this is another thing which again goes back to physics and science of the thin film. So, assume whatever you have evaporated is coming to your substrate, right. So, you can assume that whatever comes to the substrate either sticks to it and participates in the formation of the film, and the variables are distance and angle of the substrate related to the source, tilt of the substrate. You can calculate, because you know there is going to be a geometric factor on when the material is getting evaporated, how much of it is coming to the substrate. So, there will be a geometrical factor on it too, but let us say you can calculate that and you will assume that so much of it is coming on the surface, either all of it is deposited or none of it is deposited, right. So, what are the parameters that will decide that? So, this is what will happen on your surface. This all can happen or maybe one or two can happen, but let us just go through the process. So, you would have an incident growth species, which is what we have created by either E-beam or thermally heating it, which is atomic, could be in atomic form or molecules or ions. It comes to the substrate. It can, when it comes to the substrate, it is, remember, it is evaporated, so it has some thermal energy higher than what the thermal energy of the substrate is. So, there is a good chance that it does not become part of the film and it gets reflected. Okay. And if this good chance becomes 100%, you can evaporate as much as you want, nothing will form. This happens very often. If any of you have done thermal evaporation, sometimes you try to deposit gold, and if you put a glass slide, you have deposited gold, it evaporates, it goes everywhere, but on the glass slide there is nothing, right. So, the slide, so all of it is either reflected or it does not become part of the film. The other thing is that it does not get reflected, it stays on the surface, but it still has energy higher than the equilibrium energy of the film. So, it is diffusing on the surface, and we know surface diffusion is faster than the bulk diffusion. So, it can diffuse on the surface at a much faster rate, and then it has many options. It can, at some point, it can lose all its energy by collisions and other ways, and it becomes thermally accommodated. And the word thermally accommodated means that now the atom which has come, which was evaporated at a higher temperature, had a higher energy, has lost its excess energy, and it has become the same energy as the part of the film, the thin film energy, and now it become part of the film. At that point, it has become part of the film. Or it can continue to diffuse at some point, because you know that on the surface you can absorb and dissolve things. It can dissolve if the temperatures are high, and at some point it can also get absorbed as a forming a chemical bond, if there is a chemical bond possible in these two species, or getting a physisorbed or chemi-absorbed on the surface. Okay, that's how it will take place. Now, so these are the reactions that will decide how good the bonding is. I'm going to skip this. This basically tells you the uniformity, because in manufacturing, many times what is of concern is, of course, you are depositing, but what is the uniformity of what you are depositing? If I take a source here and I want to deposit this big substrate, then obviously my thickness is not uniform across, right? So one of the biggest requirement is that my thickness, which is starting from this substrate end to that substrate end, has to be uniform. So one can do a lot of geometrical calculations on that, figuring out how should I design my source such that the uniformity on the desired substrate is, let's say, within 5%, right? So there is a lot of designing that goes into designing a good thermal system for good uniformity, and these are all mostly geometrical factors and information about how the material evaporates, what is the angular distribution of the material as it evaporates. This is an example of how it would evaporate. So it is showing you here, depending on this is the distance on the substrate. So let me go back. So if this is the center point, let's say I have the source here, this is a point, center point, and this distance going away from the center point divided by the distance from the substrate to the source. If I plot that as a function of the thickness of the film that I am depositing, and then I normalize it to what I deposit right at the center, right. So this is the variation you would see if you don't do anything. You would see that at the center, if it is 100%, as you go away, and you don't have to go away too far, it's only 0.25 of the edge, the thickness starts dropping. And it is also, since you keep the material in some container, the container itself, whether it's a cylindrical one or a conical one, will decide how fast the non-uniformity takes place. So there is a lot of work that goes on in deciding how you design your source such that the uniformity, thickness uniformity is pretty good. I'll skip this again. This basically shows that you may have problems with thickness uniformity, but then one can do a lot of things from design point of view to improve that part. So I just like to discuss this particular one. You can see this. One thing you can immediately see, if you have lot of non-uniformity, the closer you will bring source to the substrate, the more non-uniformity it will be. So the farther you take the source from the substrate, it becomes more uniform. So if you want very good uniformity, and when you are in production, you want deposition taking place, throughput should be high. You want many substrate or whatever you want to deposit on, many of them go through in a shorter time, right. So one would be to keep the source very far off and then deposit on something. And the other thing would be the way it is shown here. These are the holder positions. In electronics industry, you have circular wafers. So you can, this is known as a planetary motion substrate holder. So you hold the substrate and that rotates as well as it rotates on this axis as well. So by what you are doing is that whatever non-uniformity is there as a function of distance from the source, by rotating it in all possible manner, you are averaging it out. So there are ways and means to improve such things, which is of course a technological development that goes on in these areas. The other thing I want to point out is the technique is very versatile in the sense you can do roll to roll. You don't have to do only batch to batch, you can do roll to roll, you can do evaporation on sheets. So that technique then becomes very powerful in doing manufacturing. Okay. So I will skip this because there are, if I want to deposit pure metal, there are a lot of science and material science that goes into, it's one issue, but if I want to suppose deposit alloys, right, how do I deposit alloys, and there are a lot of materials issue comes in, how much evaporation rate of one element versus evaporation of the second element, and then there are of course solutions for it also. So each of this can be talked about. I will just skip this, but just wanted to point out. So alloys will have its own feedback on how to do it and how we fix that. You can also provide continuous feed. You don't have to keep the source every time. If you want to deposit roll to roll, you are not going to remove the source, put new material. You can provide a continuous feed. Those are the technological developments in the area. So the material keeps feeding. As it's getting evaporated, new material comes in the boat and it gets evaporated. Compounds is another issue on how to get the right stoichiometry. If I want to deposit silicon oxide, how should I control the evaporation rate of silicon and oxygen present in the chamber such that I always get SiO2. I don't get something SiXO, right. So, there is again lot of material science and physics that goes into understanding how the evaporation rates and how the surface reactions are taking place. This is variations of step 2, and the first one is gas scattering evaporation. So, I just told you that when the vapor phase, the atomic form is created at a source, it should come to the substrate without getting reflected, right. And if I do that, I have a nice non-uniformity going from center to the edge. So, if I want to make it uniform, one way is also to provide scattering. So, it is line of sight right now, deposition is line of sight, start from the source, gets deposited on the substrate. But if I provide lot of scattering, this angular distribution gets more random, and that provides uniformity. So, sometimes people used to do intentional scattering, so that there is more uniformity in the deposition. Reactive evaporation, I am evaporating silicon, I put in oxygen, I will get silicon oxide in the gas phase. Plasma enhanced, and this gets into again materials issues. Let us say I want to make silicon nitride, right. I evaporate silicon, I put it in nitrogen gas, it will not form silicon nitride, right. We know that we need to have a higher temperature in order for silicon and nitrogen to react. The activation energy required is more. So, what is the way out of it is, if you make nitrogen into plasma form, what have you done? You have taken N2, you have broken it already in the plasma, it has become now nascent nitrogen atom. Now, this nitrogen atom is very likely to bind with silicon, right, and that is why with the evaporation system you create a plasma. You create a nitrogen plasma, silicon gets evaporated, it goes through that nitrogen plasma and then gets deposited. So, silicon vapors are getting created, it goes through the nitrogen plasma which has nitrogen atoms, it reacts with nitrogen atoms, and on the substrate you are depositing silicon nitride. Okay. So, that is known as the plasma enhanced, and the other name which is given to it is called activated reactive evaporation. So, you have activated it, the reaction which would not have taken place otherwise. Similarly, another technique is also known as called ion plating, which is also a thin film deposition technique. The number of thin film deposition technique is really huge, because anyone who did something in an industry or in a thing and they did something different, they gave it a new name. So, if you were to just list down all the name, they are basically variation of the same thing, but large number of techniques would come up. Okay, so I think what I will do is, in the remaining hour I will go to the second technique, which from manufacturing point is very important. So, what are the problems with evaporation? I already mentioned to you that temperature control is an issue if you are using resistive heating. Of course, solution exists, the solution exists for it, but it is very expensive. You can really control temperatures of the source and give a good evaporation rate, but then that just adds cost to it. Other issue is uniformity and surface coverage. So, you can have some solution, but still that is a big issue, because today we are going to larger area manufacturing in everywhere, wherever the economy of scale can support it, right. So, you need uniformity remains to be an issue. Contamination is an issue. When you are heating something, you are not only heating the material that you want to evaporate, you are also heating whatever is your chamber made of, whatever your holder is made of, that also evaporates. So, you get contamination. So, these are the issues which evaporation technique has inherently. Skip these things. Let me just take a minute on this. So, I was saying in the beginning that thin film deposition techniques are versatile, in the sense any material can be deposited, any thickness can be deposited. So, this kind of gives you a list. You can deposit all oxides using these techniques. You can deposit nitrides, carbides, sulfides. So, it is very good for tool coating. A lot of people are using it for tool coating and all, for hard coatings, right. So, these are very good techniques for that. Okay, so, to overcome some of the problems that evaporation has, the second physical vapor deposition technique, where the chemical reactions are not that important here, is the sputtering technique. Now, sputtering resembles basically a 3-dimensional billiard games with atoms. Okay. And how many of you have used sputtering for film deposition or in manufacturing anywhere? No? Okay. Anyway, so what it does is in sputtering, atoms are physically removed from a target. So basically, I take a target. Let's say I want to deposit aluminum film. I take an aluminum target, and I'm going to bombard that target with energetic ions, which are not going to react like argon, right? This argon atom is going to hit an aluminum atom and is going to sputter that aluminum atom, which will be deposited on a substrate. Okay. Now, the first thing which is very clear, different from evaporation, since I am sputtering off an atom, the energy of the sputtered atoms is much higher than the evaporated process, where it is only the thermal energy that is given from the evaporation, right. Now, it has impact on the film. These are generally used for hard coatings, because when you are bringing the atoms at a higher energy, they would interact with the substrate with a higher energy and get implanted in the substrate and get a better bonding and better intermix layer. Okay. So, sputtering generally is used where you need hard coating, you need good properties at the interface, because it has a higher energy, the atoms are coming at the higher energy. So, atoms are physically removed, energy is transferred from incoming ions to the target atoms to break the bonds holding the atom into a solid. That is how the sputtering process is done. So, generally in the sputtering process, a gas, typically argon, is converted to a plasma to act as a source of ion. Remote plasma ion source can also be used, or you can just create the plasma inside the chamber itself. How is a plasma made? Just like any other plasma that we use in electronics, electrons are generated in the cathode. So, it has a cathode and an anode, and they travel towards the anode, and in between there is a gas which will provide the sustenance, and the electrons collide with the gas atoms and create electrons and ions again. So, that is how the plasma is getting sustained here. This is of course the basic, maybe I can just skip that. All of you probably know how the plasma is made and sustained. You need to have enough creation of electrons and ions to sustain a stable plasma. In the schematic part, basically the sputtering of a thin film chamber would, this is only the picture of the chamber. Again, this has to be done in vacuum for the similar reasons that we did for evaporation. You do not want contamination at very high energy atoms. There is a cathode, cathode surface, and then there is a anode surface. The cathode surface is normally what you want to deposit. It is the target material. I want to deposit aluminum, it will be aluminum. I want to deposit copper, it will be copper. Argon is the working gas which I put in the chamber, and then I create by applying the DC voltage or RF voltage, I create a plasma. The argon gas in this chamber is getting ionized to argon plus, right. Argon plus will be attracted towards the cathode, and it will hit the cathode at the voltages, roughly at the voltages at which what you apply outside, and generally voltages are few hundred volts here. Okay. So, they are hitting the target pretty hard. Since they are hitting the target pretty hard, they have enough energy that this argon ion can sputter off a aluminum or copper that is there on the target. That is why it is called sputtering process. So, it is sputtering the target. Argon ions are hitting the target and they are sputtering the target. The sputtered material, now since it is it's basically those, it's like a billiards ball, the atoms are coming and hitting another target. Based on the kinematics of it, that material will come out in a particular direction, and that sputtered material, you need to place your substrate such that the sputtered material is received by the substrate, and then this material will form the film on this substrate. Okay. So, this material is sputtered and the film is being formed here. That is how the sputtering takes place in the basic concepts. Okay. Now, what is different here compared to from the point of view of what is happening on the substrate, why sputtering is considered good, especially for hard coatings, because you want a good adhesion to the substrate for hard coatings and other things. So, the difference here is that the atoms which are coming, compared to the evaporation, they are coming at a much higher energy, right. Few hundreds of volts, you are accelerating argon ion at a few hundreds of volts, it sputters an atom, the atoms which is coming out is at a much higher than the thermal energy at that temperature. Okay. So, atoms are coming at a much higher energy, because of that energy, they have an enhanced surface diffusion. Now, why is that important? When you are making a material, when you are making thin film, the more the surface diffusion you will have, the better it will be to get a smooth film. Okay? Because the atom will have a choice to, if it comes and just deposits here. I mean, just imagine for a minute that atoms don't have any mobility on the surface, and you're just bombarding them randomly using either evaporation or sputtering, and wherever they come, they get deposited. What do you think will be the resulting material? If we don't allow them to find a good place where they should get deposited, if wherever they come, wherever they hit, they just deposit there. Randomly they are coming. What would be the end material? It will be amorphous material. It will be amorphous material with lots of cavities and voids inside. It will not be a good density material. So this surface diffusion is very important for creating a dense material, dense film. So the atom comes, it has enough energy so that it looks around in the vicinity and finds, okay, this is a good place for me to bond to, and it can go to that place and make a good bonding. If you don't allow that process, then they are just coming and hitting and forming a film. It will be a low density amorphous film. But if you allow them to move, then they can nucleate, crystallize, it will be polycrystalline or even sometimes single crystal films can be deposited. Okay? So this surface diffusion is an extremely important part from the point of view of the kind of film that you want. And that is why I can, for example, let us say I am sputtering silicon. If the substrate temperature is low, the silicon that I sputtered will form an amorphous film on the substrate. I keep heating the substrate temperature. I have a heater over there. I can keep heating the temperature. From amorphous, I can make a polycrystalline. I still further heat it and provide some other activation energies. I can make single crystalline silicon using sputtering. Okay? Now that's the power of thin film deposition and the control that you have on the microstructure of the material that you are making. By changing just a substrate temperature, I can go from all the way from amorphous to single crystalline silicon. Okay, so that's the enhanced surface diffusion. This is another thing that can happen during sputtering is, let's say some materials get deposited, but the atoms which is coming to the substrate now has high enough energy that it can sputter the material also, right? And this you must have seen, I am sure you must have used these processes, plasma cleaning, right? Plasma cleaning is basically a subset of this what I am talking about. What do you do in plasma cleaning? You create a inert gas plasma and you hit the substrate by putting it at a cathode. So whatever loosely attached things are there, they will just get sputtered out. You will clean the surface, right? So that can happen on the cathode, it can also happen on the anode. So if your energy range are not right, rather than depositing a film, you will be sputtering it off. So basically there is a whole energy range. If energy range is low enough, then it would just get deposited. If you keep increasing it, it will start sputtering. If you keep increasing it further, what will happen? These ions are coming, and if you keep increasing its energy, although that is not possible in plasma, but if you could keep increasing it, that atom will go inside the material and get implanted. That is called implantation, right? So there is a whole range of how you control the energy of the species that is coming, depending on what technique you use plasma or you use a discharge gun or some other process. You can control where that atom goes and how it is interacting with the surface. Okay, so a huge range of techniques come out depending on that control. So this is the part of that implantation. So if the energy is high enough, the atom which is coming gets implanted in the device, and it is providing enough activation inside the film. And this is what makes sputtered films a lot more denser compared to the thermally evaporated films, because you continuously sort of giving it a compressive stress. The atoms are coming with high energy, they are moving all the other atoms which are there in the film. And keep in mind that what I am making it here, this is all at atomic scale. This will not be more than 10-15 angstrom into the surface. It is not at the surface, it is just in the subsurface region. Things are happening in the subsurface region which are giving your material a quality which would be maybe tensile or compressive depending on the material you are treating. Okay? And that will give you a higher density of the material. So the technique provides all this just by controlling the energy of the incoming species. I will skip this. This is about a plasma, how to strike a plasma, and what different zones of the plasma are. This I have already described. So let me just spend maybe a few minutes. The energies that we are talking about for the incoming atoms on the surface. So, if you are doing thermal evaporation, all the energies you're not going to exceed 5 electron volts. You can do that calculation on what the thermal energy, equilibrium thermal energy is, and if an atom gets evaporated, what's that energy will be. But in the case of sputtering, you in this particular case, you have either physisorption or reflection. If an atom comes with low energy, it will get accommodated or it will get reflected. If it comes at 5 to 10 electron volts, it can damage the surface. And whenever since we are talking about atom, we are talking about damage also at the atomic scale. It can migrate on the surface. If you go to a little bit higher energy, it can sputter what is there on the surface, it will sputter it off. If you go to greater than 10 electron volts, then it has capability for going below the surface also, right. So, all these processes will take place when you are making the film, and that gives you in the end a very good film in terms of the stresses in the film and what you want to do with it. So, I do not know how much time is there. Almost there, okay. So, I will just finish in a few minutes. So, sputtering as such, I think from manufacturing point of view, especially from hard coatings and from applications in the mechanical engineering area, is a very powerful technique for the deposition of thin films of a large range of compounds. That is the good advantage of sputtering. Remember in evaporation I had all these what to do with alloy, what to do with compound. In sputtering you do not have to worry so much. Whatever target you make, it will get deposited on the substrate. So, if I wanted silicon 3 carbon 4, I make that target, it will get deposited with the same ratio on the substrate. Okay. So, that is a powerful control that sputtering has compared to evaporation. Complex compounds can be deposited using relatively easy to fabricate metal targets. There is a little bit problem in poorly conducting compounds because it is a discharge. If the target is not conducting, then how do you create the plasma? And the solution is RF. By rather than doing DC supply, you do the RF supply to the plasma, and then you can sustain a plasma in even non-conducting materials. You can create coatings with the graded composition, and all those possibilities are there in the case of sputtering. Very briefly, I would touch the other end, which is non-physical vapor deposited, the chemical vapor deposition. Now, chemical vapor deposition, as I said, so there is no vapor being created. In case of physical vapor deposition, we physically heated a material or we bombarded it with the ions to create the material, right. So, that was a physical reason for the species. In case of chemical vapor deposition, the normally inlet source is a gas. So, you bring in the gas and then you control the reactions of it on a substrate by controlling the temperature, the rate at which the gas is coming. So, the gas is going to come depending on the surface property that you have chosen. It will get absorbed, it will absorb as physisorbed and then chemisorbed. It may dissolve also, and it will also form a film here, and whatever is product gases are left, they will come out. Okay. And then there can be a lot of good science in here, thermodynamics, kinetics. If you have a deposition rate which is not dependent on temperature, you are working in the mass flow control regime of a reactor. If you have a deposition rate which is heavily controlled on temperature, then you are working in the reaction rate control regime of the reactor, right. So, that is the CVD process, and again it is a very process. Where is it useful? Think of a component you want to deposit, cover it with a film, and it's a very intricate shape. It's not like a physical sheet, but it has 3D surfaces, and you want to deposit something uniformly on that surface. You cannot use a physical vapor deposition technique, because physical vapor is always line of sight. I create a physical vapor, it will go wherever the direction is and it will deposit there. But I have an intricate shape, I can heat that shape. If I can uniformly heat that shape, I bring in a gas and that particular material does react with the gases, I will form a very nice conformal film all around that shape. So, CVDs are very good for making depositions or nice coatings which are uniform on a very random shapes which may be in 3D type. I will skip this science part of it. Of course, the best way of very simple way of making any film is you take any material, heat it up in a particular thing, it will form a, depending on the material's property, it will form a film like silicon. If you heat it up, form silicon oxide, it will be nice layer. Although it depends on the material properties. Some films make a very nice uniform layer and some make a very non-uniform layer. So, you have to work on the material properties on that. So, I will skip this part and end with this thin film deposition on the substrate side. So, again there is a lot of material science that goes in here. You can have a film which it does not become continuous. Initially, since I said I am bringing atoms and they are going to get absorbed. So, if you think of at time t is equal to 0, there is nothing, then I will bring 5, 10, 15. So, first those 5 and 10 and 15 have to come together. So, they have to nucleate, then they have to grow, then only it forms a continuous film, right. And so, if you can imagine, if I take a thin film deposition technique and I do not let it become a continuous film, I just I stop it at a point where it is just nucleated, what do I get? Nanomaterial. Okay, and this is one way of making nanomaterials. People make these nanoplatinum and all they are doing is they are taking a film technique and they are stopping it, or they are freezing it basically before it becomes a continuous film, and you have these nuclei. This is the way they make nanomaterials. So, that is one way to do it. Then depending on if your material and film the properties match right, then you can actually have nice uniform films. And these are this kind of areas, and also controlling the parameters for deposition. You can have epitaxial films, means making single crystal films. Silicon single crystal films are also grown. And then sometimes you can have a combination of the two. And these are some of the problems that you normally see, and then you have to control your material, your parameters, process parameters. You would see a film not being conformal, there are voids being here, pinholes, roughness, all these could be problems depending on your application. Roughness can be bad for optical applications. So, all these issues can come up, and then you control your film deposition technique to handle that. So, let me leave you with some nice pictures. Can really control to create sculptures. This is called thin film sculptures. You can really control your deposition and how you deposit it to create structures like this. These are all tried and demonstrated, and people are finding some very nice, interesting optical applications for this. I think Dr. Anand Ramakrishnan is talking after me. He will show some more images of it.
Yes.
So, you can make this from thin film deposition by controlling the direction at which the species are coming, how are they getting deposited, and then by rotating it in the right way. Okay, so, that is very beautiful. These are all real images created by thermal evaporation and controlling it. If you are controlling the crystallinity, you can actually control the shape of what you are depositing. Very nice hexagonal shapes can be created. I will skip all this, show you one more. This is all evaporation. So, this surface, this particular cone, it is being created by a deposition technique. And the way it is created is, first you do the lithography to create this hole, right, and then now when you deposit it, the way the shadowing works, the shadowing of the incoming atom works, it deposits in the form of nice cones. So, this is all deposited because of the geometrical constraints given, the film gets deposited in nice cone. It was used for field emission arrays, for making field emission arrays of molybdenum for some display applications. So, there is a lot of maneuverability with these things. Different structures can be made where you want to make arrays and all by controlling many things in this. I think I will end with this. Thank you.
I'm sure you will have last questions, but we can take a couple of them. But interestingly, we worked on this PVD deposition for enhancing the fingerprint. So your fingerprint is there. It is very interesting. What happens is when you do a fingerprint, your fingerprint wherever is there are OH molecules. So on those places you can do a PVD coating. So it will try to enhance your thumb impression. So this can be used for even detection. Okay, so questions please.
I'm told that CVD coating is better as compared to PVD.
Not always, but for conformity, yes, CVD always works, has a more conformal, because PVD is a line of sight deposition. So, if you have very irregular shapes, CVD would be better. If you want, for example, for hard coating and other things, the sputtering and giving compressive stress or some stresses in the film, sputtering is always preferred, because you can control the stresses in the film in that. So, it depends on application.
Is there any compatibility thing between the coating and the material? Limitation of material which is going to be coated on?
Yes, so that comes from the part that whatever the substrate that you are going to start with, the incoming atom, first of all, you can make you can make a film on any substrate as long as it doesn't dissolve on that particular substrate. So there are sometimes you need to provide roughness on the surface. You can bombard the surface or maybe do the pinning and or something so that it accepts it. But if there is no chemical reaction, let's say the incoming atom, the film that you are trying to make, and the substrate doesn't form a chemisorb bond, then yes, that will remain a weak film. So if you want a stronger bond there, it will be good to use sputtering because it allows a lot of activities happening at the interface, and it also allows it will allow the chemical bond to form. That would be a good strong film that you will form. So you can make a film. It may not be very. I mean, they do sketch test, right? So if a film doesn't have good adhesion, it will scratch easily. If it has a good adhesion to the surface and it forms strong bonds, primary bonds, then it will be better. So it does depend on the. You need to choose the material and the film very carefully. You do have ways out of it. Suppose your material, your film is not compatible with the substrate, you can make a buffer film. You can put a film in between which allows, for example, gold doesn't stick to glass, but you make titanium in between, you have a good film. Any other question?
This normally only for pure metals, is it? Pure elements only can be deposited?
No, anything can be deposited. Even polymers can be deposited. The physics becomes a little bit different because now your incoming species is not a atom, but it's a molecule or a component of a molecule. So no, you can deposit anything. Even there are techniques where you deposit an organic molecule and it polymerizes as it gets deposited. So there is polymerization during deposition.
Also, you could probably mask the surface to selectively.
Yes, absolutely, and you can do selective shadowing is absolutely done, and that's one way of doing many things.
But porosity is very less.
Huh?
Porosity.
Porosity depends on substrate temperature, as I was saying. If you, for example, if you are going to make amorphous film and you are going to use PVD technique, there is a lot of line of sight effect and you can have voids. So the voids will be more. But if you go to sputtering, normally sputtering has a lot of activity in the surface interface region or the surface region where the atoms are coming. Porosities are less, densities are higher. There are a lot of studies in the sputtering area where they have measured densities using some XRD technique and all, and as a function of the bombardment energy of the atom. And you can improve it to almost close to bulk. So that depends on which technique and how you use it.